Solving systems of linear inequalities. Systems of linear inequalities is when a set of two or more linear inequalities contain two or more variables. Solutions of a system of linear inequalities is when all of the ordered pairs satisfy the linear inequalities in a system. So we're going to look at some examples here. Example 1, they want us to tell whether the ordered pair is a solution of the given system. So what we have here is an ordered pair, -1, -3, and we have two separate inequalities. We have y is less than or equal to -3x plus 1, and y is less than 2x plus 2. So first thing we need to do is take our first equation, y is less than or equal to -3x plus 1, and we're going to put this ordered pair, -1 and -3, we're going to substitute it in the inequality to see if this ordered pair, -1, -3, satisfies and is true with this linear inequality setup. So we have -1, -3, using y is less than or equal to -3x plus 1. We're going to substitute in -1 for x and -3 for y. Using ordered of operation, we have -3 times -1 is +3 plus 1, which equals 4. Is that true that -3 is less than or equal to 4? Yes, this is true, because -3 is less than or equal to 4. So now we're going to take our second equation, y is less than 2x plus 2, and we're going to substitute -1, -3 into the second equation. So we have y is less than 2x plus 2. We'll plug in -1 for x, -3 for y. 2 times -1 is -2, plus 2 is 0. Is it true that -3 is less than 0? Yes, this is true. So the ordered pair does work. It does create a solution for the two systems of linear inequality. So we can say the final answer after we've substituted and solved, -1, -3 is a solution to the system because it satisfies both inequalities, making them true. Our next example, similar situation, tell whether the ordered pair is a solution of the given system. Here we're given an ordered pair of -1, 5, two separate linear inequalities. Y is less than -2x minus 1. Y is greater than or equal to x plus 3. We'll first substitute -1, 5 into the first equation. So I have y, which is 5, is less than -2 times x, x is -1, minus 1. -2 times -1 is +2, minus 1. 2 minus 1 is 1. Is this true 5 is less than 1? No, this is a false. This is false because 5 is not less than 1. So let's look at the other situation where we substitute -1 in for x and 5 in for y for the second equation. Y, which is 5, greater than or equal to x, which is -1 plus 3. -1 plus 3 is 2. 5 is greater than or equal to 2, and this is true. But since the first setup with the first equation is false, that means that this ordered pair, -1, 5, is not a solution of this given linear inequality situation. So our final answer is -1, 5 is not a solution to the system because it does not satisfy both of the inequalities. It is not true for the first set, but it is true for the second. Since it's not true for both, then it does not satisfy the inequalities. The next example here, they're wanting us to get into graphing with the inequalities. So we're going to graph each system of linear inequalities, and then we're going to give two ordered pairs that are solutions and two that are not solutions to the graph, what we are doing here. So step number 1, we're first going to graph each system, each linear inequality. For the first one, actually we need to think of first if they're in the form of y equals mx plus b, because that's going to help us graph. Remember, we also have to think about our boundary lines. Whether it's dashed or solid. Remember, it's dashed if it's greater than or less than. It's solid if it's greater than or equal to, less than or equal to. And we're going to have to be doing some shading here. Remember, when y is greater than the equation, you shade up. When y is less than the equation, you're going to be shading down. So all of these factors that you learned from the last section are going to apply in this final section here. So let me erase these notes. You should have wrote these notes down in your notebook, but I'm erasing this so that I have room to graph this so you can see. The first linear inequality is y is less than or equal to 3. So here's my graph. To graph this y is less than or equal to 3, I'm going to start at the value 3. That's my, actually, I don't have a b here or an x. It's saying y. Think of this as y equals 3 for the first inequality. So I go to 3 on my y-axis. There's no slope. This 3 here is representing your y-intercept. So if y is less than or equal to 3, we're going to be shading everything down. For our second linear inequality, we have y is greater than negative x plus 5, so we would start on the y-axis at 5. My slope is negative x, so negative 1 over 1, which means I go down 1 to the right 1, down 1 to the right 1. Notice it's greater than. It is a dashed line because it's not equal to. Notice my dashed. Y is greater than, so I'm going to shade everything up. So after we've shaded, after we've graphed, we've put in the correct boundary line, and we've done the appropriate shading, what happens here is where you see the purple is where both of the linear inequalities will intersect one another. This is where any of the points we choose in this section of the graph, it would make both, it would be a solution to the linear inequalities. So my step 2 is we need to find an ordered pair that would satisfy both linear inequalities, but then we also need to find 2 ordered pairs that do not satisfy. So when we look at this, for step 2, when you think of 8, 1 and 6, 3, those are ordered pairs that are solutions because it would make each of these linear inequalities true. 2, 6 and negative 1, 4 are not solutions because when you do the shading does not apply for both equations. So that's why they are not solutions to this linear inequality. Looking at the next example, it says graph the systems of linear inequalities and describe the solutions. So here we have 2 linear inequalities, and we need to graph each of these and then describe the solutions. So for the first one, I'm going to graph y is greater than or equal to 3/2 x plus 1. To graph this, I would start at 1, and my slope is 3 over 2, so I'd rise 3 and go to the right 2 and put a point. And then I'd keep going up 3 to the right 2 and put another point. Notice it's greater than or equal to, so it's going to be a straight line. It's the blue line here, straight line. Y is greater than or equal to, so I'm going to be shading up for the first equation, or for the first linear inequality. The second one, I have y is less than 4x plus 3, so I would start at 3 on the y-axis. My slope now is 4, so it's rise 4, run 1, so up 4, and go to the right 1, or you could go down 4 to the left 1. It's less than, meaning it's a dashed line because it's not equals to, less than, and y is less than this, So I would shade everything down. So where did these two linear inequalities intersect with the shading? The purple again shows where both lines will meet with the shading. So what's going to be a solution? Well, at what points does the shading occur for both? Well, at 1, 3 and 2, 6. So we could say 2, 6 and 1, 3 are solutions to both of these linear inequalities. 0, 0 and negative 4, 5 are not solutions because notice they're not within the purple area. That means that the shading did not take place for both of the equations. Going on to B, again we'll graph these linear inequalities, making sure they're in the y equals mx plus b form. When I graph my first linear inequality, our starting point will be at 1. My slope is x, so it's 1 over 1. So starting at 1, I would rise 1, go to the right 1, rise 1, go to the right 1. It's y is less than or equal to, so it's a solid boundary line. And y is less than, I will shade down. The next one, it's saying y is greater than 2. Notice there's no slope for this linear inequality. There's just a y-intercept. So I will put a point at 2. It's saying y is greater than 2. Since it's greater than, it's a dashed boundary line. Y is greater than, I shade everything up. Where on this graph is it so that shading takes place with both equations? It's going to be here. The purple is where both of the shading occurs for each. So what is a solution? Well, any point within the purple area would be a solution. So 3, 3, 4, 4 are solutions, whereas negative 1, negative 4 and negative 3, 1 are not solutions.